So dear students, welcome back to our series of videos of the chapter 4. In fact, we had reached to this slide where we had one of these so-called very important slides, because we have a summary of all what we have more or less seen about the axial geometries. We have here on this central part what is called the cascade analysis. It's very useful for this kind of machines. Typically, it's like if we had a cut of the machine by a kind of cylindrical surface as we have here, and then we unfold or unwrap the surface over the 2D surface, and we get to something like this: inlet velocity triangle, outlet velocity triangle, and with the two main features for the axial geometries, which are that the u2 is equal to u1, so peripheral velocity is kept constant because omega is kept constant and r is also kept constant. And second feature, if we don't change the let's say axial variation of the surface, so tip and hub radius are are kept constant, then the second important feature is that the height of the triangle is kept also constant. All those ideas on this slide are the 1D theory summarized here by the Euler equation, and those can be expanded and are so done in the bibliography to the 2D study. For instance, who in 1952 did the division in the two main surfaces as kind of S1 and S2, S2 here being the vertical planes more or less parallel to the blades, and S1 being kind of horizontal or cylindrical surfaces for each radius, so from hub to tip radius. We could split the flow in those two surfaces, and from that on there are several studies considering that two surfaces. The main issues of the flow are, however, kept constant also for the different studies: low flow deflection and relatively high flow rate and rather small pressure increase. So normally we have to use several stages. Other possible option, and has been also developed in the bibliography, is go back to the fluid mechanics basic ideas on the lift and drag coefficients. Because typically we have a profile like this. The turbo machine is divided into different blades, and the blades in fact are kind of a stack of aerodynamic profiles, and we could for instance study the pressure and suction surface and different features of the aerodynamic performance. We are going to center our attention on the drag and lift coefficient, defined as this, D or L, over the same non-dimensional value, the same value to make it non-dimensional, which is 1/2 of rho peripheral velocity squared times the surface. And the typical shape, we have here the graph for the typical conclusion that we get from the CL and CD coefficients. Normally CL increases up to a point in which flow separates. This is due to because we are changing the angle of attack, and the angle of attack becomes critical here, so it promotes stall. And CD, which keeps growing with function of the angle of attack, in fact has a minimum. It's a kind of parabolic shape like we can see on the drawing. So this is the classical, and how this has been applied to the turbo machinery flow is done by a series of blades, systematic series, typically NACA series with 4 or 5 digits. Normally the geometry is a key parameter for the performance: curvature, thickness, chord, blade angle, twisting, and many other parameters like that. And the typical graphs that we obtain are those. So normally drag as a function of lift, and the evolution is kind of these U-shaped curves where we try to find a minimum in the drag and a maximum in the lift. So somewhere before drag starts to increase so dramatically as we can see there. Those blades, series of blades, were experimentally tested, and their performance have been plotted in many graphs like that, several graphs like that. So we have a kind of database. If we want to design a new geometry, we have a kind of very important database to compare with our let's say with our requirements. And with that on mind, we can do the two-dimensional flow. For instance, go to the forces and some definition first: solidity as the quotient between chord and pitch, and then, for instance, the number of blades by the pitch has to be equal to the perimeter that we are considering. And we have here the development of the equations that we would get if we have the cascade analysis. Here we have two examples of cascade analysis. This one, it's an horizontal layout, so flow comes from left to right, and it finds the blades here, and it leaves the blades in a kind of horizontal main direction. And that one is in a vertical, let's say, layout. Flow here comes from upward towards downward direction, and it finds the blades here. So normally in this case we have the rotor here, and then it leaves the blades also in a kind of vertical direction. We have for the forces that kind of equations that we can straightforward develop from the control volume that we have defined here by a dashed line, with the pressures at different points P2 and P1, so vertical direction, very easy to obtain. Pitch over times P1 minus P2, sorry, P2 minus P1, and then vertical force rho pitch V square times 1 over tangent beta 1 minus 1 over tangent beta 2. And if we want to project that forces on the lift and drag directions, we get to this set of equations. And for calculation purposes, a kind of average 1 over tangent beta, so medium 1 over tangent beta, is defined as this one. 1/2 of 1 over tangent beta 1 plus 1 over tangent beta 2. With that, and using the term 1/2 of rho W1 square times the chord for non-dimensional values, and grouping the y-axis forces, we can obtain this equation or equivalently this other equation. And very often the lift coefficient is normally much higher than the CD, so CL is higher than CD, so we can neglect some terms, and we can reach this term, which represents the aerodynamic load due to the blade's curvature. This is the right hand side of the equation, so that part here. And it's found for high solidity, so many blades, or due to a high lift coefficient, so an optimum profile. Remember that we have plugged the hypothesis that the CL is several times bigger than the CD. And it's a very important equation. CL times the solidity that we have previously defined equal to this term, right? Also, working with the equations, we can define the reaction degree, as we have found also for the centrifugal kind of machines like that. And here we have normally this reaction degrees gives us the idea of the energy percentage of the pressure developed by the stator or rotor. Yes, as we have seen for its definition before. Remember, it's the quotient between the pressure term over the total term of the head. And here we have the typical description of the velocity triangles, inlet and outlet for a given machine. And here on the right we have another sketch of another cascade analysis with another blades here. In this case we have stator at the inlet, and then rotor, so stator and rotor configuration, flow going down in the vertical direction, it changed to V1. Here V1 is named as C1. We have this change in nomenclature due to the book where we took this drawing from. But as you see, W1 plus U1 is equal to V1 at the inlet, and the same happens at the outlet. Outlet triangle being here, W2 plus U2 equal to V2. And with the velocity triangles, we also can define the reaction degree as in 3 steps, from 0 to 100%. So from 0 to 1, we have the typical shape that we should have on the velocity triangles to get that degree of reaction, or the reaction degree, as we mentioned that. Another example of the velocity triangles and cascade analysis, you have it here. You can work it out at home. For any questions, obviously, contact me at any time. I'm not saying that, but sure, feel free to contact me. And another approach, another idea is to use what is called the free vortex or vortex. So in fact, the vortex description that we may have, particularly if we use the equation that we have seen for the Euler equation so far, so the 1D equation, we have something like this. Remember, U times VU over G, so we have this kind of term for the theoretical head. And therefore we can solve for VU, and we have in fact a constant over the radius. And this is the kind of let's say vortex description that we are imposing along the machine. So this is kind of idea to change from hub to tip in the velocity profile. And we could choose another idea. For instance, we could choose the fourth vortex. Fourth vortex is given here. It's a constant times radius instead of a constant over radius. And you have the 2 descriptions here of the velocity profile. So let's say that we can change apart from the aerodynamic profile, which was the discussion so far, and the velocity triangles, we can also change the velocity distribution from hub to tip, and this is what will tell us about the vortex that we have. Also, there are solutions in the practice that there are a combination of both vortexes, so a combination of a free vortex plus a forced vortex. And then to complement the 1D or 2D theories, we have the same ideas as for the centrifugal flow machines. We have the not ideal or perfectly guidance of the flow. So we have the slip triangle idea, the same as we have developed in previous slides on this chapter 4. And also we have the wakes, jet wake pattern here. You see here again the cascade analysis, inlet velocity triangle, outlet velocity triangle, and in fact we have as 2 velocity triangles because we have the jet and the wake velocity triangle. Normally on this kind of geometries there are some approximate equations for the flow deviation, and it can be an equation like this with some parameters there that we have already seen. Curvature through the parameter k, in this case beta 2 minus beta 1, and the other coefficients for the rotor and stator, m and n, are defined as this. So they are kind of empirical equations that we have in the books, right? And if we want to study the total or global 3D flow on the axial machine, we have to consider many other ideas, as for instance those horseshoe and tip vortex interaction, vorticity mainly generated at the boundary layer, possible separation of the flow, and possible wakes. And you have a picture here, a kind of full picture of all those ideas. We have the tip vortex here, we have the horseshoe vortex, which happens to occur here in the hub. Normally on the hub we have as a corner flow here because we have the hub and also the blade as boundary conditions for the flow. So we have this kind of rotating path, right? At the tip we have the same. We have the gap, the axial gap here, sorry, the radial gap from the tip to the casing, and this is the full picture, so you can have a look at it.